All right, guys, today we are going to go over empirical and molecular formulas. So we first need to go over what the difference is between the two, and we'll do some examples in order to show that. So when we are given the name of a compound, like dinitrogen tetrafluoride, the molecular formula is telling us how many of each atom is present in the compound. So di means two, so two nitrogens. Tetra means four, just four fluorines. Now, if you need a refresher on how to name compounds, please check out my video linked above on naming ionic and covalent compounds. So this is telling us that there are two nitrogens and four fluorines in our compound. When we are talking about the empirical formula is the most reduced formula. So we're reducing it down to its lowest possible ratio. So because the 2 and the 4 are both divisible by 2, the empirical formula for this would be NF2. So your empirical formula is just the reduced version of your molecular formula. Let's take a look at another example. Calcium chloride. This is an ionic compound. So again, if you need a refresher on naming ionic compounds, please check out the video that's linked above. Calcium and chlorine. Now, because calcium has a +2 charge and chlorine has a -1 charge, the correct formula is CaCl2. This is telling me that there is one calcium and two chlorines. Those are not both divisible, therefore it is currently in its most reduced form. That means that my empirical and molecular formula are the same for this particular compound. Now that we understand the terminology, we can use some problems to figure out the empirical and the molecular formula if we are given percent composition of a compound. Let's take a look at an example. All right, our first problem is what is the empirical formula of a compound that is composed of 64.8% carbon, 13.6% hydrogen, and 21.6% oxygen? The easiest way to approach this is to assume that rather than percents, that we have grams. Now, if we know that percents are always out of 100, we can assume that if our sample was 100 grams, 64.8 grams would be carbon. That means that 13.6 grams would be hydrogen and 21.6 grams would be oxygen. So again, when you're given percents, just assume that your sample size is 100 grams, and that will make things much easier. Now, when we are talking about formulas, remember that the formula is telling us how many of each atom are in the compound. But that ratio can also be scaled up. That ratio can also tell us how many moles are in the compound. Let's go back to our original problem. So in this formula, it is telling me that there are two nitrogens for every 4 fluorines. That means that there are 2 moles of nitrogen for every 4 moles of oxygen. It's a 2-to-4 ratio. Likewise, in this formula, calcium to chlorine, we know that there's 1 calcium for every 2 chlorines. We can scale that up and say that there's 1 mole of calcium for every 2 moles of chlorines. So these formulas work in the unit of moles, but not in the unit of grams. So when we come back to this problem, if we're trying to find the ratio between the carbon, the hydrogen, and the oxygen in order to get the formula, it is important that we are in the unit of moles, not grams. That means that we're going to need to do a conversion here. I'm going to start by taking my 64.8 grams of carbon and converting that into moles. I can do that using the molar mass on the periodic table, which is 12 grams of carbon per 1 mole of carbon. When I do the conversion, that gives me 5.4 moles of carbon. We're going to do the same thing for the hydrogen and the oxygen. I know that I have 13.6 grams of hydrogen, and I'm going to convert that into moles of hydrogen. That gives me 13.46 moles. I'm going to do the same thing with my oxygen, the last element in this compound. And when I go to the periodic table, there are 16 grams of oxygen in 1 mole of oxygen. That gives me 1.35 moles. Remember that our formulas are always written in moles, but they are in whole number ratios. And right now we have a 5.4 to 3.46 to 1.35 ratio. We need to reduce this into its lowest possible ratio. The easiest way to do that is once you have all of your substances in the unit of moles, simply divide by the smallest one. So my lowest number here is 1.35. I'm going to divide this by 1.35 in order to make my lowest number a 1. But now I'm going to have to divide all of these by 1.35. That is going to give me the lowest possible whole number ratio between them. All right, when I divide all of these numbers by 1.35, or the lowest number of moles, notice that it sets everything to 1. So now I know that I have 1 oxygen for every 10 hydrogens for every 4 carbons. We are going to write this out as a formula now that we are in whole numbers. So there are 4 carbons. This tells me that there are 10 hydrogens, and there's only 1 oxygen. I don't need to write the 1 there. This is my empirical formula. So that is the lowest whole number ratio that we can get for each of the elements in the compound in the unit of moles. We have our empirical formula. We need to figure out our molecular formula. So in order to find the molecular formula, we can use the molar mass. It tells us that the molar mass of this compound is 148.2 grams per mole, and it wants to know what is the molecular formula. All right, I like to set up a little grid here to help me organize my information. The EF stands for the empirical formula. I'm going to write in the empirical formula that I found from above, C4H10O. Now, I also know that the molar mass of this compound is 148.2 grams per mole. So when it's talking about the molar mass, that is referring to the molecular formula. So if I can find out how much mass is in my empirical formula, it can help me find my molecular formula. In order to find the mass from my empirical formula, I'm going to add up 4 carbons using the mass on the periodic table, 10 hydrogens. All right, I'm going to add up the mass off the periodic table, multiply it by the number I have, and I end up with 74.1 grams per mole. That is the mass of my C4H10O. Now I know the molecular formula has to be in the same exact ratio as my empirical, so it should be a multiple. So if I take a look at 74 and 148, I can see that I simply need to multiply by 2 in order to get my molecular formula from my empirical. So if I have to multiply the mass by 2, that means that I'm going to need to multiply the formula by 2 as well. That's going to give me C8H20O2 as my molecular formula. All right, we are going to use the same steps, but we are going to do one problem that's slightly more complex because our ratios don't come out perfectly when we convert to moles. So let's take a look at a second, little harder example, but the process again will be the same. All right, this time we have a compound that contains 69.94% iron and 30.06% oxygen. Once again, the first step is to deal in grams instead of percents. The easiest way to do that is to assume that you have a 100-gram sample anytime you have a percent. That means that I would have 69.94 grams of iron out of a 100-gram sample. Likewise, I would have 30.06 grams of oxygen out of a 100-gram sample. All right, so remember that whenever we are writing formulas, empirical or molecular, the formulas need to be in ratios in the units of moles. So since we're in grams, we're going to have to first convert these into moles using the molar mass on the periodic table. I'm going to set up my dimensional analysis, and the periodic table tells me that there are 55.85 grams of Fe for every 1 mole of Fe. So now I know that I have 1.252 moles of Fe. I'm going to do the same thing with my oxygen. I want to take these grams of oxygen and get the exact same amount expressed in moles. So the periodic table tells me that there are 16 grams of oxygen in 1 mole of oxygen. When I do the math, I get 1.879 moles of oxygen. But remember that our formulas, both empirical and molecular, need to be written in whole number ratios. So right now, I'm in the correct unit, the unit of moles, but I'm not in a whole number ratio. So the easiest way to get a whole number ratio is to take the smallest number of moles, the 1.252, and divide by itself. That will give me 1. Now I'm going to have to divide my other number by the 1.252 as well in order to keep the ratio the same. This time, when I do that, I get 1.5. Notice that my numbers are better, but they are still not whole number ratios. This happens sometimes, but I can't write a formula as FE1O 1.5. I need to keep this ratio the same, but it needs to be expressed in a whole number. The easiest way to do this, if you have this problem, is to just simply get this 1.5 to a whole number by multiplying by 2. Whatever you do to one substance, you need to do to the other as well. That means that the lowest ratio between the two is a 2 to 3 ratio this time. Now, if you end up with something that is, let's say, 1.25 or 2.25, you can simply multiply both numbers by 4 in order to get them to a whole number ratio. Likewise, if you have 1.33, you could multiply by 3 in order to get that to a whole number as well. So now that I have the lowest whole number ratio in moles, I'm ready to express the empirical formula. This is telling me that there are 2 FEs for every 3 oxygens. My empirical formula is Fe2O3. I hope that helped clear up the difference between empirical molecular formulas and how to calculate them from mass percents. Thanks for watching, and be sure to check out my other videos.